Okay, so we gradually start. Okay, so let me it is my great honor to introduce Professor Yoshiyuki Kagei from Tokyo Institute of Technology. Let me briefly mention his career. He received PhD from in 1994 from Hiroshima University under the guidance of Professor Miyakawa. And then his major topic is Navier-Stokes, compressible and incompressible both. And he moved to Kyushu University and become professor there. And then he moved to Tokyo Institute of Technology. And he won several prizes from Math Society of Japan, including Analysis Prize. And he's also invited to spend several years in Germany as a Humboldt Fellow. And so today, he's a specialist of special stability analysis of the Navier-Stokes equation. Today, he's going to talk on stability and bifurcation analysis of the compressible Navier-Stokes equation. Please.
Thank you very much. Thank you for introduction. And I also would like to thank the organizers for kind invitation, especially Professor Giga, for kindly inviting me to this very nice seminar. So it's great contribution to this field under this COVID situation. We can have communications among our fields. Okay, so let me start. Today, I'm going to talk about mainly bifurcation analysis of the compressible Navier-Stokes equations. And I firstly consider the Taylor-Couette problem as an example, and then finally, I give some remarks on the bifurcation stability analysis. Okay, so firstly, consider the Taylor-Couette problem, and consider the infinitely long cylinders with concentric okay, these two cylinders, but these are both infinitely long. And now we have discussed compressible fluid between these two cylinders, and assume that the inner cylinder rotates with uniform velocity, angular velocity omega, and the outer one, for simplicity, is at rest. So it does not move. Then, as you can easily imagine, that the fluid also rotates, accompanying with the rotation of the inner cylinders, and you can observe this kind of laminar flow. And in fact, this is stably observed when the angular speed of inner cylinder omega is sufficiently small. And this laminar flow is called the Couette flow. And when omega increases, the angular velocity increases, then you have centrifugal force, and this force becomes stronger, and therefore the fluid inner part tend to move to the outer part. So you have this tendency. But you also have the wall of the outer cylinder. And therefore, when omega is not so large, then this Couette flow is still stable. But beyond some value of omega, this centrifugal force becomes dominant, and you have this kind of patterns, wave flow patterns. So this is the so-called Taylor vortex. So the fluid rotates in this direction. Also, some vortex patterns observed, which is periodic in the axis of the cylinders. This is the so-called Taylor vortex. And this phenomena can be formulated mathematically as a bifurcation problem for the fundamental equations of the fluid mechanics. So let me formulate this phenomena in a mathematical way. So I assume that the fluid is viscous compressible, and the flow is barotropic type. So the governing equations, the system of equations, these two equations. The first one is so-called continuity equation. Time derivative of rho plus divergence of rho v is equal to 0. And here, unknown functions are the density rho and the velocity field v. And the second equation describes is the equation of motion. So the first term here, rho times time derivative of v plus v gradient v. This is the acceleration of the fluid. And here you have viscosity force, and P denotes the pressure. Here I assume that the pressure is a function of the density only. It does not depend on the temperature. And I assume also P is a smooth function of rho, and at rho equal to 1, the derivative of P is just normalized as 1. And later, I will consider the situation where the density rho is quite close to 1. Okay, here several parameters appeared. New and new prime are the viscosity coefficients, which are assumed to be positive, roughly speaking. And you also have here the Mach number, epsilon, which is positive. And in this talk, I will consider the situation where this Mach number is sufficiently small. So in some sense, the situation is quite close to the incompressible regime. But when epsilon is positive, then the system here is classified in a quadrilinear, hyperbolic, and parabolic system. So the solution exhibits both hyperbolic and parabolic aspects. Okay. So in our problem, Taylor-Couette problem, this system of equations is considered in a cylindrical coordinates, the domain omega alpha, which is, okay, in the cylindrical coordinates r, theta, z. Z is the direction of the axis, and the domain is between two cylinders. So R, the range of R is between R1 and R2, and theta, azimuthal variable, this just 2 pi, 0 to pi. And in the direction of the axis z direction, I impose a periodic boundary condition. So we consider this periodic box for this system of equations. This is because the Taylor vortex has the periodic patterns, which is periodic in z direction. And boundary conditions on the lateral cylinders is the azimuthal component v theta at the inner cylinder is just normalized to 1. So this is due to the non-dimensionalization. And firstly, the cylinder, inner cylinder, rotates as a speed in a speed of omega. But now here I make non-dimensionalization in such a way that this angular velocity becomes just 1. And the effect of omega is put into the here, the viscosity coefficient. It's a kind of the inverse of Reynolds number. So you have here, omega is proportional to the inverse of nu. Okay. So if omega increases, then it corresponds to the decreasing of nu. Okay. Then you can easily see that this system of equation has a simple form of stationary solution, which I call the compressible Couette flow. This has the following form. The density component, which I denote by rho epsilon c, is just the function of r only, and it's close to 1 when the Mach number epsilon this number epsilon is sufficiently small. And the velocity field v theta, this represents the rotating rate, and it has only theta component and depends only on r, and which in fact has this form, the linear combination of r and 1 over r. This flow profile is also the stationary solution of the incompressible Navier-Stokes equation. So then you can easily show that if nu is sufficiently large, in other words, omega, the angular velocity omega is sufficiently small, and also the Mach number is sufficiently small, then this Couette flow is asymptotically stable. So the question is now, what happens when nu decreases? In other words, the angular velocity omega increases. Okay. So before proceeding further, I would like to give a comment on the relation between the compressible and the incompressible Navier-Stokes equations. So here we consider the density rho. Its variation is quite small. So 1 plus epsilon squared times phi. Rho has this form. Epsilon is sufficiently small. Then substitute this form of rho into the compressible Navier-Stokes equations. here, this equation. Then you have equation, system of equation like this for phi and the velocity field v. Then letting epsilon to 0 formally, then the first term and the third term in the continuity equation vanishes. So you have divergence b equal to 0 incompressibility condition. And then in the second equation, rho goes to converges to 1, and the divergence b is just shown to be 0. And as for the pressure term, here you have only gradient phi remains. So as a consequence, you have this system of equations, which is just incompressible Navier-Stokes equation. So when epsilon is sufficiently small, you could expect that the behavior of solution of the compressible Navier-Stokes equations could be approximated by the incompressible Navier-Stokes equations. But of course, this is a singular limit, so it's not straightforward to conclude such approximations. Okay, so as I said, also the velocity field of the Couette flow is just a stationary solution of this incompressible Navier-Stokes equation. Okay, so let me consider the incompressible problem. Now we consider the stability of the Couette flow. So the perturbation of the Couette flow is denoted by W, and the corresponding perturbation of the pressure is denoted by P. Then you have this system of equations, divergence W equal to 0, and here the Navier-Stokes equation with these lower order terms. And these terms will cause instability of the basic flow BC when nu is okay. It's competition of this disturbance lower order terms to this viscosity coefficient. So when nu is sufficiently large, then this viscous term is dominant to this instability term, lower order term, while when nu decreases, then at some point, at some value of nu c, these lower order terms becomes dominant, and you have instability. In fact, a long time ago, bifurcation, this instability was already shown by Felte and Yudovich firstly, and then Kirchhoff and Zorga considered some stability problem. And in summary, you have the following. There exists some critical angular velocity, which I denote by nu c. If nu is greater than this critical number nu c, then the Couette flow is stable. On the other hand, if nu is less than nu c, then the Couette flow becomes unstable, and Taylor vortex pattern bifurcates from the Couette flow, and near the bifurcation point, nu equal to nu c, the bifurcating Taylor vortex is stable. So this just suggests the Navier-Stokes equation describes well the real phenomena. Okay. So more precisely in a mathematical setting, so I denote by the linearized operator bold L nu. Nu is a bifurcation parameter, and we restrict the problem onto the divergence-free vector fields. So I denote it by L2 sigma and under some symmetric condition. So P here is a Helmholtz projection to the divergence-free vector field space. And we consider this operator, Stokes operator with lower order perturbation term on L2 space, whose domain is H2 and H01. 0 means on the lateral boundaries, perturbation is 0. And we also impose symmetric symmetry condition, reflection symmetry. Okay, with respect to the plane z equal to 0. So this means that r and theta components of the velocity field is just even functions in z, while z component is an odd function, an odd function of z. So if you impose this symmetry, then at the criticality nu equal to nu c, the operator, linearized operator, has a kernel which has one dimension. Okay, then I make the following assumption on the spectrum of the linearized operator. So the spectrum of the linearized operator minus L nu lies in the strict left half plane, except one point spectrum, which I denote by lambda nu. And this lambda nu depends analytically on the parameter nu. And when nu decreases, then this lambda nu moves to right, and at some critical value, nu c, this eigenvalue crosses the origin from left to right. So maybe it's better to write a figure. So you have complex plane. Sorry. Here. And the spectrum minus L nu lies in this part, which is strictly away from the imaginary axis. And there is one simple eigenvalue, lambda nu. And when nu decreases, then this lambda nu moves to right. And at nu equal to nu c, so this lambda nu crosses the origin. So this is the assumption on the spectrum of for the incompressible problem. Okay, as for this assumption, I'd like to make some remarks. And Felde and Udovich showed that there exists a critical value, lambda c, at which the one simple eigenvalue crosses the origin. like this. But the direction is of the crossment is not known. So you have this one. This depends on the wave number alpha. So we have considered the situation like this, and in z direction, we impose the periodic boundary condition like this, and one period is just 2 pi over alpha, this alpha. So the spectrum, of course, depends on this alpha. And for almost all alpha, Ferti and Udovich proved that one simple eigenvalue crosses the origins. Okay. So next, next remark is that the direction of this movement of lambda. So numerical computations and experiments support that lambda nu crosses the origin from left to right. Okay. So I make this assumption. Then you can easily imagine that some stationary bifurcation occurs, and let me consider the stationary problem. It's written in this form. Here the linear part and the nonlinear part term is here. And this W is the perturbation of the Couette flow. Therefore, W equal to 0 is just the solution of trivial solution of this system, which represents the Couette flow. And then standard bifurcation theory, for example, by Crandall-Rabinowitz, shows that there exists a bifurcation, which in fact describes the bifurcation of the Taylor vortex. And you have the following. Under the assumption A, there exists a non-trivial stationary solution, which I denote by W delta because it depends on the small parameter of this stationary problem. For the value of nu, which is close to nu c, the critical value nu c, and the deviation of nu from nu c is denoted by eta delta, and eta delta has this form, minus a times delta squared. Delta is a small parameter, and a is a positive constant, and the solution W itself has this form, delta times some function W0 plus delta times capital W. Here, W0 is a function which is an eigenfunction for nu L nu with nu equal to the critical value nu c. And the capital W is just over the 1 when delta goes to 0. This capital W also depends on delta, but it's over the 1. So you have a non-trivial stationary solution of this incompressible stationary problem, which is the leading part, whose leading part is just given by the eigenfunction for the zero eigenvalue of the linearized operator L nu with nu equal to the critical value nu c. Okay, so the bifurcation diagram is written in the following way. So you always have here, okay, here I denote by I take the omega as a bifurcation parameter, which is just the inverse of nu. And then you always have the solution Couette flow for any number of omega, numbers of omega. And then there exists a critical value, which which I denote by nu c. This is just almost like 1 over nu c. Then beyond this value of omega c, you have non-trivial solution. It's just a Taylor vortex. And as a result of the standard bifurcation theory. So, I'm sorry. So now you have here eta delta is just deviation from nu c. It's just here A is positive, and therefore in the inverse you have omega. Omega is just omega c なんだったっけ plus something A delta square higher order term. Therefore, the non-trivial solution appears just for omega. Here A is positive, greater than omega c. So bifurcation occurs in this direction. Then the standard bifurcation theory states that the stability of the solution is like this. Below omega c, the Couette flow is stable. And beyond the omega c, the Couette flow becomes unstable. Instead, the Taylor vortex gets the stability here, stable. Okay, so this is the situation of the incompressible problem. Now I'd like to consider the compressible problem. The equation is just written in this way, which I already write down. And nu is just the same as before. And we have epsilon. This is a Mach number. And I'd like to consider the situation where this epsilon is sufficiently small. Okay. So since I'd like to consider the stability of the Taylor vortex, Couette flow. So therefore, I rewrite the equations into the one for the perturbation. The density perturbation here, I scale epsilon squared because I'd like to consider the situation where the perturbation is sufficiently close to rho epsilon c, which is just 1 plus over the epsilon square. So the situation where I'd like to consider is just the regime is quite close to the incompressible one. And the velocity perturbation is denoted by simply W. Okay, then the system of equations for the perturbation phi and W is written in this form. Okay, here I collect all of linear terms on the left-hand side, and the right-hand side denotes the nonlinear terms. And in the equation of motion, the right-hand side takes the form, okay, G, I denote by G. The G has the form minus gradient, W gradient W. This is just over the one. And all the remaining terms has the coefficient epsilon squared. And here it includes U, phi and W, and the derivative of phi and W, and second order derivative of W. Okay. So here nonlinearity includes, because of the system is quasi-linear, so nonlinearity includes the principal part. The first equation divergence phi W, which includes the gradient of phi. So this is the highest order term for phi. And here for W, we have second order derivative. Okay, so okay, anyway, so now we let epsilon to 0. Then the rho c epsilon goes to 1 as before. Therefore, you have the first equation multiplying the epsilon square to both sides. Then you have divergence W equal to 0. As was the second equation, rho c epsilon tends to 1. And you have here minus nu times Laplacian W. And divergence W equal to 0. And okay, here pressure term. This goes to P prime 1 of 1 times phi. But I assume that P prime 1 is just normalized as 1. So you get pressure term gradient phi. And nonlinearity, you get here only minus W gradient W. So you have here also you have the incompressible Navier-Stokes equation. So you could expect that the similar bifurcation phenomena occurs also in the compressible problem. But some technical difficulty appears in this continuity equation. Here, this is the first order equation in the density perturbation of phi, and therefore this part causes a derivative loss in the usual setting. So it's not pressure differentiable in a standard setting. Okay. On the other hand, here also in the motion equation of motions, the second order derivative of W appears, but the principal part is the elliptic operator. So this term is not harmless. Okay. So now consider the linearized problem. Okay, I consider the linearized problem in the following setting, L2 setting, with under some symmetries. So linearized operator has this form when some symmetric conditions are imposed. Okay, so as before, I impose a reflection symmetry with respect to z equal to 0 plane. And also, here also I impose axisymmetric conditions on the perturbation. So this is, of course, satisfied by the Taylor vortex. And therefore, it's sufficient to consider the bifurcation of the Taylor vortex. But of course, not for the stability problem. Okay, anyway, I impose the axisymmetric condition. Then, okay, linearized part, here you have this one. Then if you impose the axisymmetric condition, then this term vanishes. So the linearized operator has this form. Here the convection term disappears, and these 1 over square epsilon square divergence, and here gradient operator, these forms, these two terms form first order symmetric operators. And here you have elliptic operator, strongly elliptic operator with lower order terms. And for the density perturbation phi, I impose the vanishing mean value conditions, which is of course coming from the conservation of mass. Okay, this symmetric assumption is some technical reason I will explain later. Okay, then as for the spectrum, you have the following. Okay, I will explain. So there, the spectrum decomposed into two parts. One lies strictly away from the imaginary axis, of course, in the left half plane. And the other one is there exists one simple eigenvalue near the imaginary axis, which I denote by lambda epsilon nu, when epsilon is sufficiently small. And if nu decreases, then this critical eigenvalue lambda epsilon nu moves from left to right, and at some critical value, nu equal to nu epsilon c, this eigenvalue crosses the origin from left to right. And this critical number, nu epsilon c, is close to the incompressible critical number, nu c. The deviation is just over the epsilon square. So you can show this phenomena for the spectrum. Okay, let me give an outline of the proof.そうか、これもう46分。I'm sorry, already 46 minutes. Okay, the spectrum, when epsilon is small enough, then the spectrum near the imaginary axis decomposed into two parts.
You have 4 minutes.
Oh, thank you. Okay. Two parts. Just I did not S1, S2. Here, S1 is just near the origin, and this part is given by a perturbation of the incompressible spectrum. So as for the incompressible spectrum, you have just only one eigenvalue. And this part is given by a perturbation. So you have one critical eigenvalue. And the other parts, S2 part, is just these parts is just whose imaginary part over the epsilon inverse, which comes from the acoustic waves. The acoustic waves has the propagating speed just over the epsilon inverse. And then if we, okay, I was able to show that under the axisymmetric assumptions, these acoustic wave parts rise in the stable part. So I used this axisymmetric assumption only to show these acoustic part rise in the stable part. Okay, of course, the question is if you consider non-axisymmetric perturbations, what happens this part? Okay. Okay. Anyway, one simple eigenvalue crosses the imaginary axis. Then you can show the bifurcation. Even though this part is not freshly differentiable, you have the same bifurcation of stationary Taylor vortex, whose principal part is just the eigenfunction of the linearized operator for the zero eigenvalue at the critical part. Critical, I forget epsilon here. You see epsilon. And here I consider the, okay, anyway, before incompressible problem, the dependence of the bifurcation parameter and also the function in the on the parameter delta is analytic, but the compressible problem, it's not analytic in general, and we need to construct in the higher order Sobolev spaces, and the smoothness of the solutions bifurcating branch depends on the smoothness of this function spaces. And also you have the convergence of the compressible bifurcating solution in this way. Okay, so the bifurcation diagram is just the same as before. And the idea of the proof is just here in the continuity equation, you have this first order principal part. Therefore, this is not freshly differentiable. In a standard way, if you use a standard method, you invert this equation, okay, quite roughly speaking, then you get this one. If you find non-trivial fixed point, then you have non-trivial solution. But this inverse has the estimate, this one. So density component is just hk to hk. The velocity component, it has a smoothing effect. Therefore, hk minus 1 to hk plus 1. So two orders you get. Now you apply this estimates to this NUU, then you have the divergence of phi w hk norm, but then you have derivative loss. So this method does not work. Therefore, we put this nonlinear term in the principal part and consider the equation of this one. And solve this equation, if you, okay, now give here un minus 1, and then consider this operator, then you get some iteration scheme. And finally, you get the solution. Okay, so okay, and now I skipped something. And as for the stability, now I could consider only the axisymmetric perturbation. And then here, when delta is sufficiently small, this term vanishes. But this also has delta times something like W epsilon delta gradient phi. This is the first order, the principal, this also principal part. Therefore, it's not a regular perturbation in this term. But in this case, also you can show that the principal eigenvalue is just given by this form, which is a perturbation of the incompressible problem. As for the eigenvalue, you can show that it's a perturbation, but the eigenprojection is not a perturbation. Okay, maybe I should stop here. Thank you for your attention.
Thank you very much for your wonderful talk. Are there any questions? If you have a question, please unmute or raise your hand. Okay, let me have one. Let me ask one question.
Yes.
In your setting, outer cylinder is fixed, right? Outer
Yes.
boundary fixed. If
Yes.
if your outer boundary is rotating, it can be reduced to this current situation. If outer boundary rotate.
Outer boundary, if you move the outer boundary, then the direction of the movement, if it's opposite, then you have Hopf bifurcation. So that the situation becomes quite different. And in this case, you can construct a framework of the Hopf bifurcation for the compressible problem, but it's quite difficult to consider the convergence of the solution branch as epsilon goes to 0. This is a very interesting problem, I think.
Thank you very much. Are there any further questions? If not the case, I think time is already over. So we would like to thank speaker again. Thank you very much for your wonderful
Thank you very
talk.
much.
Thank you very much. And each of you should have received an email with an invitation to the coffee break. please feel free to join us there with your favorite drink.
Yeah, thank you.
Thank you very much.
I close the session.
Yes.
Yes.
Thank you,
Thank
Yoshikazu.
you.
Thank you,
Thank
Yoshi.
you, Daniel. Thank you, Jessica.
Thank you again.